So welcome to this new edition of the new Athena X-ray Advances Science webinar. Today we are lucky to have count with us Mauro Dadina. He got his degree in 1996 in Bologna, where he also made his PhD. Then he moved to Rome to what is when he worked with the Berkeley Science Operations Center. Then in 2000 he went back to the what now is IAPS enough in Rome, and then to Bologna, which is now enough for us, but he's still there. He kept working on EPIC and on board and XMM-Newton. He's been working in Integral as well, and he's been involved in some proto missions, some of which look familiar also to me. He's been working on UFOs since 2004. And he's been part of the Athena X-IFU science advisory team, and he's now co-I of the consortium. And he's going to talk to us now about what we learn and what we will learn, hopefully, soon on UFOs and on AGN. And now, Mauro, please.
Thank you. Thank you very much, Francisco, for this introduction. And in this talk, I will try to convince you at the end that Athena or New Athena will offer interesting opportunities in the future in study the ultra fast outflows in AGNs. But before starting, I have to underline a couple of caveats. First of all, I guess that we are, or mostly of us are really curious to know what are the first CRISM resolve results on this topic. I won't touch any of these because I don't know anything of this. I hope that you can appreciate my courage in giving this webinar without knowing anything about the CRISM resolve results. And secondly, this presentation will be strongly biased toward my point of view. That means that it will be strongly X-ray centered. Okay, so let's start talking about the oops, it doesn't move. Incredible. Okay, here it is. Let's start explaining what we are talking about when we talk about fast outflows in the X-ray spectra of AGNs. The presence of such a component in the core of the AGNs manifest themselves essentially as a deep absorption feature due to highly ionized matter. The strongest between these features are typically the ones due to iron in its hydrogen-like form. And they were discovered in such form back in 2002 when the first really convincing evidence of such outflows were reported by Chandra and collaborator studying the X-ray spectrum of a rather distant QSO, APM08, QSO at redshift 3.9, that was also a magnified source. Given the energy at which these absorption features were measured, the author were able to understand that along the line of sight was present an outflowing component made of at least two different components traveling with two different velocity of the order of 0.2 and 0.46. That means that these outflowing winds present in this object was moving with velocities order of magnitudes larger than the one already known to be characteristics of the standard warm absorber usually observed in the X-ray spectra of AGNs. 1 year later, Pons and collaborator found a similar spectral feature in the spectrum of PG1211, an aeroline CFET1 in the nearby universe. But in this case, the authors were able to detect not only the high energy component of the wind in the form of the typical iron K absorption feature, but also absorption feature due to lighter elements that were detected not only using the EPIC CCD data, but also using the grating data. As it was the case for APM-08, also in this case, the observed outflows appear to be to display a rather complex structure with characteristics due to different components moving at different velocity and with different ionization states. In the same years, this collaborator reported the very first evidences of a similar outflows in PDS-456, an intermediate redshift QSO, that has become, after the discovery, something like the Rosetta Stone to study the ultra-fast outflow, because it is one of the few, if not the only sources for which we are able to detect UFO signatures whenever we use a telescope, an X-ray telescope to observe. And as it was for PG-1211, also in this case, the absorption feature measured both with EPIC and the grating display rather complex structures. As it was observed then, and also with later observation, the outflows measured in this object is quite complex, made of at least two outflows components traveling at 0.25, 0.4 C. But during the years, it also show eclipsing phenomena, evidences of reflection of the primary emission coming directly from the inner walls of the winds and other stars. As soon after the discovery, these winds has been literally injected by theoreticians into the models of galaxy evolution to explain some newly obtained results that appear to link strongly the fate of the supermassive black hole to the characteristics of the bulge of the galaxies that were hosting these supermassive black holes, but also the fact that the observed luminosity function of the galaxies depart significantly from what expected from the standard lambda CDM model. And the basic idea that the theoreticians assumed was that if these winds were energetic enough, they could impact on the star formation history of the host galaxies so as to switch on some kind of feedback mechanism able to create an interconnection between the tiny supermassive black hole and the properties of the host galaxies. When we say that this wind must be energetic enough, the theoreticians tell us that the kinetic luminosity, the energy injected into the host galaxies must be of the order of 1% of the bolometric luminosity. That means that they could have a cosmological impact, interesting cosmological impact. Let's add another ingredient to the already needed ingredient that we had to collect in order to understand what is the astrophysical importance of these winds. Because if we want to, it is now clear that if you want to understand what is in details the accretion ejection cycle at the center of the AGNs, we had to add also this wind that could be not negligible from an energetic point of view, but this is not enough if we want to understand what is the impact that these winds can have on cosmological states. Together with the good determination of the physical and geometrical properties of this wind, we now are requested also to have a good determination of their properties along cosmic time so as to understand if these components could be effective in shaping the star formation history of the host galaxies. Now, indeed, soon after the discovery of the first evidences, convincing evidences of the existence of this wind, some sort of hunting for such features started, and in relatively few years we were able to add to the original free object a series of galaxies. mostly of which were nearby and bright Cipher galaxies. Indeed, if we see what are the objects in which, for the very first time, we were able to detect UFO signature, we noticed that there are essentially very bright Cipher galaxies in the nearby universe. For instance, EC 4329A is one of the brightest Cipher galaxies, plus a couple of distant QSO, which detection was reported by Chapas, that were both lensed, so magnified in X-rays. That means that the statistics, as usual, play an important role when we are going to study this kind of phenomena. And indeed, if we try to paint a picture of what we know about this event, we end up to notice that essentially all the information that we have come from a relatively small sample of AGN that are the one highlighted here in blue, yellow, and purple, plus some other, that as this plot here, published by Matteo Italia in 2023, report in the lower panel, are characterized by the fact that they are essentially all the sources, this is true for XMM-Newton, that display, that allowed us to collect a huge number of count in the 4 to 10 keV band rest frame. That is the observational limit that we have in order to perform meaningful population studies of such kind of winds. In particular, in blue, you see the sample of objects that were originally included in the work done by Francesco Tombesi et al. Here in Bologna in 2010. That is a sample of nearby AGN, largely overlapping with the sample published in 2013 by Goffer and collaborators that used, instead of XMM-Newton data as done by Francesco, Sudaku data, but the samples are essentially almost identical. As almost identical the sample in objects published by Igo et al. In 2020, that instead of using the standard spectroscopy technique to investigate the UFO characteristics, used a timing technique. In yellow here, you see the sample of objects at intermediate redshift that we used to fill the gap between the sample of nearby object and the sample of IV lensed sources that we published with George Arpes et al. In 2021. That is the outcome of a large program that has been submitted with PI Marcella Brusa here from Bologna, and that was awarded of observation time of 1.8 megasecond by XMM-Newton. As I told before, we investigated also with George Arpes the possibility to use the lensed sources to investigate the characteristics of UFOs high redshift. I want to mention here that we have been awarded recently of an heritage program with XMM-Newton of 2.3 megasecond to observe also 15 high redshift objects, not lensed. We redshift includes between 2 and 4, more or less, so as to investigate the possible. This project has been tuned so as to have, as reported here, the right amount of counts in the energy where the iron feature should respect it. Here, just to complete, you see what are the distribution of all the source detected with XMM. This is the 3 XMM sample. As you can see, independently of the redshift, we are forced to work with the object that allow us to collect the largest number of distribution. And this is one of the results that we obtained in 2010, analyzing the nearby object. One of the results, of the important results that obtained Francesco in 2010 was that this signature of the possible presence of outflows were not some exotic results given given to some exotic sources, but were quite common characteristics of nearby AGNs. Starting from a sample of 42 objects, collecting more than 100 observations of these 42 objects, we were able to have a clear detection of UFO signature. By instance, the term UFOs was created in this work for 15 of the 42 objects, with an equivalent width and intensity of the line quite smaller when compared, for instance, for the typical emission lines known to exist in the spectrum of this object. The average equivalent width measured in this work was of the order of the social line related to the UFOs was of the order of 50-60. On the other hand, the velocity recorded could be quite smaller with respect with the first one detected in the quasar, but also as high as the one recorded in QSO at high redshift. You see that we recorded velocity up to 0.3 the speed of light. Another important result obtained in this paper is that these features, whenever present, are not stable, are not constant. Here, for instance, in the case of Markarian 509, in which you can see in terms of confidence contour that we observed, we detected the line in only 3 out of the then available observation. But if you watch carefully, I'm sorry, probably it is not so easy to understand, the energy at which these lines were recorded are slightly different, even between the 3 observations that show the presence of such line. Similar results have been very recently published by Gabi Matteo et al. About the sample of intermediate QSO in the subway sample, as it was the case for the nearby CFAT. Also, at intermediate redshift, we were able to prove that this kind of phenomenon, the outflows, is not an exotic effect. We were able to positively detect after a wonderful treatment of the data made by Gabi in 7 out of the 22 QSO that were part of the sample, with characteristics that are somehow bridging the properties of what has been observed in terms of velocity, what has been observed in the samples at the lower redshift, and the one that I will show you later have been observed in the sample of a very high redshift and length QSO. If you have a look here, the average velocity measured by the subways is well consistent with what measured with in the nearby sample, but there are few sources that are reaching velocity of 0.3. And finally, the program that we put together to study high redshift sources were based in a 2-step approach. The first one was to simply point the brightest distant QSO length so as to be sure to collect enough count in the new energy band where the possible UFO signature were expected. We were lucky to observe a UFO signature in one of the first 2 objects, NGJ, while we didn't see anything in another. It is important to note that both these are radio-loud quasars. After this first step, George Chartas proposed a more focused strategy to point to a sample of length, but also narrow social line QSO, already known to show strong blue-shifted calcium-4 signature in the spectra. And this turned out to be extremely quite too efficient in detecting UFO signature, because of the 13 sources selected in this way, we were able to detect the UFO signature in 12 of them. So the problem is to understand if this increasing in the detection rate of UFOs is due to a selection effect that we are introducing, or indeed indicated that the UFOs are more common going to high redshift. But let's take this for another step further. But what we learned since now putting together all this information, well, we already can say that at the first glance, these results are telling us that whatever the origin of these fast outflows, the geometry of these outflows must be quasi-spherical. And this is a quite simple outcome of the fact that the rate of detection of these winds are quite high. We are not speaking of an highly collimated object. And this is in accordance with what has been measured in PDS-456, the best, the Rosetta Stone for this kind of study by Dadina et al. In 2015, where using a simultaneous observation of PDS-456 with XMM-Newton and Nustar, they were able to model the pitching profile observed around the energy of the iron line and infer an opening angle of the intervening outflow of the order of 2 pi. That means not well collimated. On the other hand, the typical range in which the column density, the velocity, and also the ionization state of this object are well within the parameter that we were able to observe since the beginning. Moreover, we also confirmed in all the samples that these features not only are there, but are variable in time, maybe indicating that the complexity could also, of the winds could also be due to the fact that we can have a clumpiness within the winds of very complex structure. But one thing that I want to stress here is that the number of objects that we know show ultra fast outflow signature are quite small. If we take into account only the 3 samples reported here, we are talking of about 40 objects. A recent paper by Yamada and collaborators says that if we perform a deep search in the literature, we are going to end up with a sample of 80 sources from redshift 0 to redshift 4, 5, showing ultra-fast outflow signatures. That means that overall, we can already say that the sample of objects on which we are basing our results are not huge. And this could be a problem when dealing with the possible selection in faith and so on and so forth. What about other important results? Well, one of the most important results has been obviously the fact that having this sample of objects, we can now say that at least for what concerns the vast majority of the objects that are measured at non-negligible redshift, we can observe energetics that are indeed indicating that these winds can, in principle, affect the life, the star formation history of the host galaxies. Even if I want to stress here that, in general, what we are measuring here, some extrapolation using very simple X-star tables that assume spherical expansion and so on and so forth. That means that we have to make a rather large number of assumptions in order to establish the real energetic. Moreover, if we have a simple look at this plot, it is clear that when we move to higher redshift, we are introducing probably some selection effect because we are measuring higher column density. That means intrinsically deeper absorption feature. So we are not sure, we are quite sure that our vision can be strongly affected by selection effect when we are dealing with these results. Nonetheless, we were able also to obtain other interesting results. And one of these is the possibility to have some information about the launching mechanism. Gavin Matteo et al. In 2017 already published this interesting plot obtained using the data of PDS-456, in which he clearly demonstrated that the recorded outflow velocity in this object was a function of the luminosity state, X-ray luminosity state of the object, which is something that also George Harp as a collaborator we found in 2021 analyzing together the low redshift sample, finding that the outflows velocity was well correlated with a very similar relation to outflow velocity to the luminosity of the source. And this was assumed to be the indication, the possible indication that the mechanism acting at the center of the AGN launching this wind would be due to radiation-driven winds. The basic idea is quite simple. The stronger the radiation field, the stronger the push of this field, and the stronger the velocity recorded. Nonetheless, it is fair to say that also magnetically driven wind can reproduce some variability of this kind. And to be honest, if we consider only the high redshift objects in the Charters et al. 2021 paper, only the lensed object, we find a rather different correlation, clearly indicating that the NHD model there seems not to be the major player. It is important to note that the understanding the mechanism, the launching mechanism of this object is important not only to going back to understand what is the physics of the accretion ejection process, but can have important outcome also in our ability to understand what is the real energetic. As I told you before, we are using, generally speaking, only quite simple X-star spherical models to understand, to model, to infer information about the energetic of the objects. That means that, in principle, if the geometry is not a sphere, what we get as a velocity is by definition an upper limit, a lower limit, sorry, because any projection effect, to be simple, is not taken into account. On the other hand, if we have clues about the emission mechanism, the launching mechanism, we can use the information to build up models that, with a limited number of parameters, allow us to infer the true energetic of the wave. This is the case, for instance, of this model put together by Stuart Sim et al., Costa PhD thesis in 2019, that is based essentially on a radiatively driven wind that can be tailored using different opening angle. It assumes a mechanical outflow. It assumes as a fixed parameter only the aperture and the radius of the inner winds. Given this, the other mechanical parameter of the winds can be, in principle, derived directly from the spectra. And this exercise has been done in a couple of objects already done. I want to present here the result that Valentina Bright, a collaborator, obtained studying the object MCZ03, a type 2 cipher in the nearby universe. Using this modeling, they were able to infer directly the mass outflow rate, but also the inclination angle and the final velocity of the flow. That means they were able, in principle, to fully characterize the dynamics of the winds. To test what are the opportunities open in this field with new Athena and the X-IFU in particular, I took the observation 4, this one, the blue one here, and I tried to infer what are the capabilities that the new telescope allow us to obtain if working. I used the latest specification, 13 rows, and is the resolution for AV. And as you can see, with a simple 10 kilosecond, which is a fifth of the typical exposure with XMM-Newton and the NuStar together, I was able to obtain a extremely fine determination of the characteristic of the outflows measuring this way. The only parameter for which I was not able to obtain a very good parameterization is essentially the ionization state, because I have at disposal only tables with the needed high resolution. Athena would request high resolution models for luminosity above 0.5 the editor luminosity. The production of these tables and the model in the future will be extremely high consuming for high resolution instruments. And I strongly suggest you to have a look at the Mauro et al. 2022 paper in which machine learning technique for the development of these models are presented. We did exactly the same exercise, not using NCZ, but using a typical type 1 CFET in the local universe, but using this time AMHD model produced by Keigo Fukumura. And you can see that assuming a very complex underlying continuum that contains also 3 Warner solver, we were clearly able to detect on the entire energy range the features due to the MHD-driven magnetically launched. Not only that, but in 10 kiloseconds for a relatively bright object, we are clearly able to detect the typical shape that are predicted for the absorption line when the wind is launched via a magnetic blend for pain mechanism. You see these red tail lines, which is a typical expectation for such kind of mechanism to be compared, for instance, for some setup for the radiation-driven winds in which it seems that the predicted lines are exactly shaped in the reverse way. So the high resolution, it is important not only because we can use it to define the spectra, but find good assessment of the parameter of the spectrum, but maybe also to discriminate between the different launching mechanisms. Obviously, it was the case for the disk wind. Also, in this case, we have been demonstrated that we will be able to infer all the parameter, physical parameter of the wind, so as to be able to understand what is the real energetics. Finally, again, also in this case, I talked about the fact that we use a very complex underlying model. This is the spectra expected due to the 3 warm absorbers that are typically observed in the nearby universe. You see how they will appear when observed with Athena X-IFU. This will be a huge problem to properly model that. I strongly encourage you to have a look at the paper by Barredo Porque on how new techniques are necessary and how we'll have to improve them to be able to extract the information that we are going to have with this kind of text. Last step, what about the possibility to fill the gap of the selection effect that we are having now? To answer this question, I simply try to understand what is the possibility to observe at high redshift the typical wind that we are observing now at low redshift. So I use the same extra table adopted to analyze the subway sample, and I moved it at higher redshift, knowing that what is expected that moving it at higher redshift means that the strongest expected feature is going where the efficiency of detection of our instrument is increasing, but not only that, because of the redshift, the width of the line due to the turbulent velocity decrease at a level in which we will need X-IFU to fully characterize if present any shape information of the lines. So what happens when we move at high redshift? The exercise that I did is quite simple. I take this subway table, I move it at this redshift that you see here. I tested different fluxes. For each flux, I made 500 simulation, again, using the latest setup for Athena X-IFU. For each simulated spectra, I made a simple absorption power law fitting, and then on top of that, I added a Gaussian, and I searched for all the every time that I had a delta C above 13.26, again, I strongly encourage the people to have a look at the paper by Barre Cap in 2019 to understand why we'll be forced to use with this kind of instrument the C statistic, even when we have huge statistics. That is something that is not useful for normal for us. And then I determine the minimum flux at which we can do this kind of study whenever we can detect this kind of feature in at least 99% of the 500 simulation detectors. What I obtain is something like that. These are 2 spectra took by chance in the 500 and no, more than 2,000 simulation for each redshift. You see not only the feature that moves in energy, but it shrink going to our energy. And I obtained obviously as expected that the minimum flux indeed decreased because of the play of the effective area moving at a redshift. We can clearly see the effects of the features in the response matrix. The decreasing is not monotonical, but what I get is that we have an exquisite definition, obviously, of the outflow velocity. This is the standard deviation of the distribution of the energy recorded, and you see that is one standard deviation is 1 part of the 1,000 of the measured energy. But we were also able to have a wonderful definition of the width of the line that strongly suggests the possibility that at this level of fluxes, that is not very low, because we are talking of the order of 1 times 10 to the -10 in the observed 2 to 10 energy band. We can have also information about the shape of the line. So we can hope to perform this kind. The last question at this point is how many of sources of these flux are known today? Well, a first answer will come directly probably from the Wi-Fi survey, because this is for 100 square degrees. The survey, original survey, I guess it will be smaller. Anyway, there are expected some tens of sources up to redshift 2.53 discovered by the survey itself. But it's interesting to note that we already have some meaningful sample of such possible targets, because if we cross-match the 4XMM catalog with the medium QSO, we already obtain hundreds of possible counterparts at redshift above 3. And to conclude, I hope that I convinced you that Athena XRISM, new Athena XRISM will be interesting. Even if that, I guess, we are all curious to know what are the results that are going to come from CRISM resolve. It is true that CRISM resolve, I guess, will be fundamental in answering some of the questions that I presented here, especially about the structure of the wings. If you think that, for instance, the possibility that there will be clamps, narrow feature will be easily detectable in bright object that is resolved, but also the shape of the line. And so I have some insights on the launching mechanism as well. It is true that even CRISM resolve will benefit usually if they will be able to remove the problem due to the gate valve, so as to have also the collecting area below to a key. But I guess I'm convinced that the new result by CRISM will further highlight the fact that we are going to need an instrument like Athena, new Athena X-IFU, because I guess it will be the only chance that we'll have to really test the physics, the astrophysics, but also the cosmology of large sample of this kind of objects, not only in the local universe, but also in the distant universe across cosmic times. Finally, I have to say that in the actual situation, only Athena XRISM will allow some timing technique, and I must admit that I'm really curious to understand what CRISM will be able to do in solar mass compact objects. And that's it. Thank you very much for your attention.
Thank you, Mauro, for this nice talk and opening to us the exciting world of UFOs in AGN and what we are going to learn about them. So are there any questions? Don't see any questions or the chat. I hope Sylvia will help me with the chat if something appears there. Okay. So since I don't see any, I'm going to ask you to be a bit more daring and make some what do you think is gonna be discovered by XRISM? What would you hope that is discovered by XRISM that will direct new science?
I guess that there are two fields that, speaking about UFOs, in which XRISM will be a game changer soon. One obviously is to understand if the shape of these lines have some indication of the dynamics of the wind, that means which kind of mechanism is acting to launch that. But also, I guess but also I guess that it will be a very good instrument to understand if there are clampings within. There have been a lot of not speculation, observations that suggest that this wind can have diffuse continuous flows with embedded denser clouds. This kind of scenario is perfectly suited to be studied also with XRISM in the actual working condition, I guess, because in this case the clouds should produce narrower feature, and so easier to be recorded, even if with a somehow limited collecting area, the energy of the iron core band.
Okay, I'm sure we're looking forward to it. But, I think there is a question from the New Athena Science Study team. You can open your microphone and camera if you wish.
Can you hear me, Francisco?
Yep.
Hi, it's Matteo. By the way, I am here with all the members of a New Athena study team. We have the first meeting today, so yeah, we are actually 15 in the room. So my question, Mauro, first of all, thanks for the presentation. Very clear, very close to my heart, very exciting. My question is on the determination of the outflow mass and therefore kinetic energy and outflow rates. These estimates are dependent on the exact geometry of the outflow. And as you stressed, we have no idea now what the geometry is. And so we use, for instance, a spherical expansion, but we don't know actually what the true geometry is. So, and these may introduce a factor of a few uncertainty, at least in the determination of the outflow rates. What is in your view? Can we actually, with the spectroscopy data or maybe timing spectroscopy, pinpoint more exactly the structure, so the shape of the outflow, and therefore reduce the systematic uncertainties on the determination of the potential outflow parameters?
I guess that we certainly can strongly reduce the uncertainties using both techniques. Obviously, having timing information means have a direct determination of the dimension of the region in which the absorption occurs. Together with that, once we are able to understand what is the emission mechanism, we can tailor the models that we are using. Now, to be honest, I know that also in the models that we use, there are some parameters that are fixed. For instance, the opening angle of the flows, but also the opening angle of the flows, and also the distance at which these winds are launched. Okay, but it is also true that this parameter can be changed, and we can study how this can affect the outcome in terms of the line. I guess the coupling of the two can help. To be honest, I'm not sure that we can be perfectly sure at the end of what we are going to end up, because the tests that I made are based on a couple of setup, and I don't know exactly, because we didn't try too many different setups on that. But I guess that the coupling of the two will give information that are no less than certain than the one that we are obtaining by now. I guess that we are thinking usually that we are not doing something too extreme because we are using a simplified assumption, but the simplified assumption is strong. It's very strong. The spherical expansion is also. So that's what I can say by now. We need water to be sure.
Thank you.
I hope
Any other
I answered,
questions?
honestly.
Okay, so I think there is one question in Q&A. You can open your microphone and speak if you wish.
Hello, hi. My name is Jiang. I don't know if you can hear me. Is that okay?
Yeah.
Great, thank you. Thank you so much about the presentation. It was very good. I was just wondering about this MHD wind model you were describing, and it seems like it would be great if you can detect some line shapes. I'm just wondering if these galactic black hole X-ray binary wings are MHD wings as well. Can you use the existing Chandra grating data, which also have a really good spectral resolution? Can you use these data to constrain these MHD wind models?
I know I'm not deeply involved in this kind of study, in this kind of object, but to what I know, I'm concerned. I know that Keigo is working. Keigo Fukumura is actually working on this data. So
Okay.
I know that they are working on that. To be honest, I'm not sure if they are using with success. They are using grating data. To be honest, I guess that probably Chandra grating now are not the best way to go because of the problems. Are you thinking about the high energy gratings?
Yes, the high energy grating.
Yes.
I mean, of course, with XRISM would be great, but I'm just thinking because Chandra data are already public there, and people like John Miller, and they have shown this great, amazing absorption lines in X-ray binaries, and I'm just wondering if there's line shape, can we use these data to constrain the line shapes?
To be honest, I don't know exactly the literature on this kind of objects, and I'm sorry.
Right, that's okay. Don't worry. Yeah, thank you very much. Thank you.
You're welcome. Thank you.
Okay, so I don't see any more questions. Okay, so before closing, just one more question and one announcement. So the question is, do you think that, because we've heard a lot about the atomic databases not being enough for the upcoming data, what do you think? Is
I think
there
that
gonna
it will be a further problem. Yes, of course. You see that, for instance, for the determination of the single, very simplified absorption line that I simulated up to redshift 5 in sources that, I mean, we were able to determine in the sample one part of over 1,000, more even better. That means that at 2 eV, we are 2 kV, we are dealing with problems of the order of DeV. And so, yes, it will be a problem. I know that many groups are already working. I guess that it was a problem with the ETOMI data. I don't know how they are facing now. I guess I know that they are facing it with XRISM, and it will be even worse for the XIFU data, of course. Yes, that's something that we need to have to fix before the launching of the Athena.
Okay, thank you, Mauro, for your answers and the very nice talk. And now thank everybody for attending. And just before we close this session, just announce you that we will close for summer the webinars, and the next one will be on the 3rd of September by Katia Poppenherger from Potsdam University, talking about mysteries of exoplanets and low mass stars and how to shed new X-ray light on them. And with that, we close this session and have a nice summer.
Bye.